you can see it's called the second fundamental theorem of calculus. So like it's almost as important as the first one, right? Probably just as important, but it is called second fundamental theorem of calculus. And I will tell you that when I first learned this, I didn't like it. It was not my favorite. And it was really because it wasn't taught in a very good way. And I'm hoping, because now I really like it. I actually think it's cool, and it's interesting, and I'm hoping that I can teach it in a way that you will understand it right away instead of like 10 years later. So let's see if we can do that. So when we had talked about derivatives, right? We were able to define them as a function. Say I gave you the function f of x equals x squared. Then we said we didn't just only find the slope at one spot. We found the slope anywhere we wanted to in terms of x, right? F prime of x is 2x. So I could find the slope anywhere on that function using this derivative function. So is there something we could do the same way as with an integral? So like if you look at this first piece here, what we've been doing is kind of like just like you would compare it to finding the slope at one spot. We're finding one area. This definite integral is from the area from A to B. It's a constant, or sorry, A and B are constants. The answer is a number, right? It's the area. So how would we make that more of a function? So let's kind of look at that. We called it capital F of x equals the integral from a to x of f of t dt. So notice this function, capital F of x, the input is x. That goes there. So if I wanted to find capital F of 3, this would turn into integral from a to 3 of f of t dt. So what it's doing is whatever my starting value is a, I've got a function that lets me find the area under some graph f of t from a to whatever that x value is. Like 3 would be from a to 3. 10 would be from a to 10. A would be a constant again, so maybe that's 0, maybe it's 1, maybe it's 40. Right? And then because we're now like I'm calling this function f of x, and that x is going there, I can't use x again. So that's like for a lot of people, like where did the t come from is one of the hardest parts of this. Like it's just it's just a way to not use x again. Right? We can't use x to represent two different things, so we need a different variable name. So like now the function we're graphing and finding the area underneath, we're saying is f of t. And the function that is the area from a to some value, that's where the x is coming. So I know it's you will still, but try not to get too hung up on the fact that it's t. It's just a second. It's just we're naming this in a different way. Okay, so let's what does this mean? Let's take first the function t. Right, and what I should we get another mislabeled axis here. This should be t. So function t is this line of the slope of 1 goes through the origin. So this integral function, capital F of x, is the area underneath this line, between this line and the x-axis, starting at 1, going to any x value we want, or I should put any t value we want. And we calculate like that t value is determined by whatever we plug in for x. So if I said f of, we can do it, f of 1 would be the integral from 1 to 1 of t dt. Just be 0. No area there. What about capital F of 2? The integral from 1 to 2 t dt. Oh, that's this. Right? So we could go old school and just do our area formula, right? So if I wanted to go the geometry route, I would say that this is 1/2 times 1 times 1 plus 2. There's my area of a trapezoid. That's 3/2. And like that worked, right? 1.5. 3/2. 1.5. Okay. I can also do it with our new definite integrals for fundamental theorem of calculus rules. Right? I could say I know the antiderivative of t is t squared over 2 from 1 to 2. And then I could evaluate that. That's plug in 2 first. 2 squared over 2. Subtract, plug in 1. 1 squared over 2. That's 4/2. Minus 1/2 is 3/2. Oh, same answer. What if I did f of 5? Pick one of those two ways. I don't care if you do it geometry or new school, fundamental theorem of calculus. What would f of 5 be? Send me a chat when you got it. Lots of good answers. I think everyone I've seen is correct. Yeah. And that's the key here. It's the integral from 1 to 5 now of t t. Evaluate that. T squared over 2 from 1 to 5. So 25/2 minus 1/2. That's 24/2, which is 12. So there's a question that's probably a good question. I'm just picking problems for us to try here, like to try to understand what this is. There's no rhyme or reason to why I picked 1, 2, and 5. We just those are examples for us to do. And so like you can see, and maybe I should like, let's do this. Let's call it F5 would be this area. So capital F of x is now a function that lets us calculate the area from 1 to some x value, whatever it is. And so what happens next is we take the derivative. We have a function now, f of x, capital F of x. What if we take the derivative of it? Well, let's see. Let's start with that function. And up above here, we evaluated it at certain points, 2, 5. But we could evaluate this in terms of x. So I'm going to do my definite integral, t squared over 2, evaluated from 1 to x, instead of like 1 to 4, 1 to 5, it's 1 to x. And so I plug in x first, x squared over 2, subtract, plug in 1 squared over 2. So I now have that f of x, if they evaluated the integral, is equal to x squared over 2 minus a half. So while I didn't know how to take the derivative of this, I can take the derivative of this. We got to turn on our derivative brains. Doing so many integrals, now we're going to go back to derivatives. Right, derivative, bring the exponent in front, right? Subtract 1. So 2x to the first over 2. Derivative of a half is 0, right? Derivative of a constant is 0. So it's just, okay, so that f prime of x is just x. Yes, that was just t. The derivative is just x. Do another one. Example 1 on the next page. We've got f of x equals, capital F of x equals integral from 1 to x of cosine t dt. Could evaluate that integral. Derivative gives me cosine. Right? Sine of t, I'm still using t, from 1 to x. On the top, plug in the bottom. Sine of x minus sine of 1. That's capital F of x. What's the derivative? X equals derivative of sine, cosine. Derivative of, well, sine of 1 is just a number, just a constant. Oh, that'd be 0. That's my derivative. Hopefully we've talked about it enough and like we're seeing this connection that the derivative and the integral are like inverses of each other, right? They undo each other. I have a function, I take its derivative, and then take its integral, I'm like back to where I started, right? The derivative and the integral are inverses. They undo each other. And so if I'm going to take the derivative of an integral, it kind of should make sense in a way that we just get what was inside. We get the integrand. The derivative of an integral is just that inside piece, which is really nice. Now there's this, like, what's happening is sort of like that x is like falling into the spot where the t was. And it's not magic, it's what's happening here. Like, that's why we're going through this process, right? If f of x is this integral, I can evaluate it and say, oh, f of x is also sine of x minus sine of 1. And then when I take that derivative, this piece goes away, and that's how now it's in terms of x. What we needed f prime of x. Well, what if that top piece is not just x anymore? What if it's x squared? Let's see what happens. One more of these. What's the integral of e to the t?
It's still e to the t.
Yeah, so e to the t. 1 x squared this time. So that's e to the x squared minus e to the first. F of x equals e to the x squared minus e. Again, its own almost looks kind of funny. E to the first. Derivative right. Prime of x derivative of e is itself. Is there anything else to do here?
Times 2x.
Times 2x. Why?
Because you do like e to the u times u when taking the derivative, right?
Yeah. Remember what rule that is? That's our chain rule, right? Yeah, there you go. Chain rule. That's chain rule. Yeah. So when we did this derivative here, take the derivative of e to the x squared. It is e to the x squared times the derivative of the inside, which is 2x. So this time it's not quite matching perfectly. 2x e to the x squared. Here's my original. Is that. So what's happening is that because when I take this derivative now, that upper bound isn't just x. The derivative of x is just 1, right? But here, this is as a derivative, the x squared, its derivative is 2x. So when I made it e to the x squared, I'm also going to need to multiply by the derivative of that, which is 2x. So that leads us to our formula. A couple versions of it here. We need f to be continuous. Then the derivative of the integral e to x, f of t dt is just f of x. In other words, we don't have to keep doing this part. We can use this pattern. It is a pattern. We literally can just drop the x in, f of x, the derivative of the integral f of x. But if the upper limit is something fancier than just x, we have to do chain rule. So we get the second version of this. Which really, I tend not to even think about that one, just because this way we don't forget about the chain rule. And then a little note at the bottom, we need the upper limit to be the variable. So if it's not, switch them. And to switch the limits, you make it negative, the opposite of integral from a to x. Okay, so real quick, number one, I want to evaluate this as the derivative of that integral. I check my bound goes from 0 to x. The derivative of that, I can just drop the x in. It's literally just square root of x squared minus 1. Done. Question I got was, does the f being capitalized mean anything? Not really. It's often we use the capital F to represent like the antiderivative. And so that's why, because this is an integral function, a lot of times it's represented with a capital letter because it's like going backwards to the original. Number 3, we'll skip to 3. Find the slope of. It just means take the derivative, right? Derivative of the integral from pi over 2 to x cubed of cosine of t squared dt. Guess what? We don't have to go through that process of like, what's the antiderivative? We can just plug in from there. The derivative of the integral is just going to be that function, cosine of t squared, evaluated at x cubed. But because it's x cubed, I then have to multiply, I have to do chain rule. So it's going to be cosine of t squared, plug in x cubed. So it's x cubed squared times the derivative of that x cubed, 3x squared. Derivative of the thing we plugged in. And so I would probably rewrite this as 3x squared cosine of x to the 6. We made it. We'll kind of, the next stuff, it's also really good. And there are good AP problems coming up next. We'll work on that next week. Be on the lookout for directions for what we'll do on Monday. Again, I'll try to get it out to you a little bit earlier if you want to do it over the weekend. Otherwise, have a really good weekend. We'll see you on Wednesday. Bye.
Thank you.
Thank
Thanks,
you.
Crawford. Have a good weekend. Thank you.
Thanks.
Thank you.